Alright, so the last bit of our proof topic. So today we're going to look at inequalities in graphs. We have seen bits of this idea already. For instance, if I wanted to solve this sort of inequality, I could do it by using a graph. Again, I'm not suggesting this is the best way of doing it, but it is certainly quite possible to do it this way. So if I was to draw x squared divided by x plus 2, so I've drawn in the two construction lines there. The red one is y equals x squared, obviously. The blue one is x plus 2. So I'm going to be dividing the x squared by the x plus 2. So what do we know? We know there'll be a vertical asymptote at -2. What else can I work out? I know, there we go, there's our boundaries, because I can say I'm going to have a positive times a negative, so it'll be negative over here. Then it goes positive times positive for the rest of it. So I know it'll be positive there. The other thing is we're going to have an x-intercept, although I haven't plotted it yet, but there must be an x-intercept there, mustn't there, at the origin, because we'd have 0 divided by x plus 2. Okay, there is an oblique asymptote. Let's work out what that is. I could rewrite that as x minus 2 minus 4 on x plus 2. So therefore there is an oblique asymptote at x minus 2. Draw that in. Okay, we know we bend towards the asymptotes. We've got to go through the origin and stay in my pink regions. There's our graph, the dark blue one. Let me just get rid of the pink so it makes it a bit easier to see in the construction graph. So, okay, there's our blue graph. We want to know when that graph is below my red line that I've just drawn in, y equals 1. Now, of course, the problem with this sort of technique is you really need an accurate graph. Now, fortunately, I have a very accurate graph because obviously I used some graphing software to do it. But if you're just doing it on pen and paper, unless you get incredibly lucky, you might not know where those points of intersection are. Hence, you would need to solve them simultaneously. And surprise, surprise, there you go. Turns out to be x equals 2 and x equals minus 1. So when are we below? There we go, when x is less than -2, certainly the blue curve's below the red line, but also in between -1 and 2. As I say, probably not the most efficient way of solving that problem, but if it was part of a bigger question where maybe in the first part they've said, sketch this curve, well then it might be a useful way of doing it to save some time. But mind you, as I say, we've still got to find those points of intersection. We've also seen this type of question. This is more likely an extension 2 type question, although we did see it in the integration, but it's this idea of playing with the inner rectangles and the outer rectangles to create inequalities. So 1990 paper this comes from, and I think we might have even done a similar question in the textbook, if I recall. But anyway, consider the graph y equals the square root of x, and they've drawn it up nicely for us. Show that the graph is increasing for all x is greater than or equal to 0. Well, we know it's going to be increasing when the derivative is positive. So if I differentiate the square root of x, I get 1 on 2 root x, and that's certainly going to be positive. So I know whenever x is greater than 0, yep, it's positive. So it will be increasing. Yeah, I might have gone a little bit too far here. I said, well, that's great. That's when x is greater than 0. What happens at x equals 0? So at x equals 0, y is 0. So therefore, when x is greater than 0, y must be greater than 0. We can see it in our graph. It's continually increasing, so I can include the 0 as well. I don't know that I really need that last point, but there you go. The curve is increasing for x is greater than or equal to 0. Hence, show that. So now we're playing with the areas. There's the graph again, so I can illustrate what we're going to do here. So we know that our curve is continually increasing, and we can also see from our graph there that the area of the outer rectangles will always be greater than or equal to the area under the curve. So my outer rectangles, they've all got a width of 1, and the height would be, well, function 1 plus function 2 and so on. So it's square root of 1, square root of 2, up to the square root of n. So that's got that part of the inequality. Now we actually have to work out the integral from 0 to n of root x. And yes, indeed, that turns out to be 2/3 n root n. All right, so we've got part B. Now, they want us to use induction to go and show this inequation. All right, so prove it true for 1. Left-hand side, square root of 1, which is 1. Right-hand side, we get 7 on 6. So, yep, true for n equals 1. Assume it's true for k, where k is some positive integer. So there's my assumption. And we want to prove for k plus 1. And again, I'm going to use the idea of let's move it to the left-hand side there and try and show that's always negative. So there's our expression, but then I've rewritten it as the k plus 1th term plus the sum to k. And our assumption was the sum to k. So now I've got some algebra that I can play with. Well, we've got a common denominator of 6, first of all. And the other thing I did was to create a whole surd with this first one. Because remember, we're trying to prove something is a multiple of roots k plus 1. So I didn't bother doing it with the second surd because it's already root k plus 1. But the first one, I need to create root k plus 1 there. So when I make it an entire surd, we get 4k plus 3 squared times k. I don't immediately see it, so let's expand the whole thing out. I get 16k cubed, 24k squared, 9k. Well, k plus 1's not going to go into that, but if I do my polynomial division, what I do get is k plus 1, so I'll divide it by the k plus 1. I get 16k squared plus 8k plus 1, but I get a remainder of -1. But fortunately, we're not playing with an equality, we're trying to prove an inequation here. So I can now make this statement, because clearly the second last line here must be less than the last line, because the difference is in the second last line I've subtracted 1. So it must be something smaller. So I can say that that second last line is less than the last line. I've now got my root k plus 1, and nicely the second factor, is that a perfect square? I think it is, isn't it? Yes, it is. It's 4k plus 1 squared. So I can now factorise that to be 4k plus 1 root k plus 1 minus 4k plus 1 root k plus 1, which is equal to 0. So if I read down my list of working out here, it was all equals, but then at some point I've got a less than. So it must be true that my opening expression here is less than my final expression here of 0. Okay. And if it's less than, it must be true to say it's less than or equal to. In this case, it's less than. Hence it is true, etc., etc., etc. All right. Use B and C to estimate. We want the square root of 10,000. All right. We have now trapped, or as often they use the term, sandwiched the expression between two ends of an equation. So if I sub in 10,000 and evaluate to the nearest 100, well, to the nearest 100, both ends of this inequation are the same. So therefore there's only one logical conclusion, and that's that expression to the nearest 100 would be 666,700. We're going to prove x is greater than sine x. So x will always be greater than sine x when x is positive. All right, let's draw a graph. There's y equals x. There's y equals sine x. It would be lovely to say, oh, look at the picture. We've got to do a bit more than that. All right. What do I know? I know function x is equal to x. Its derivative is 1. For the sine curve, now we haven't actually seen this yet, but we will see it in the next topic. But the derivative of sine turns out to be cosine. But we're just looking for in between 0 and pi on 2 just for this first bit. If we look at just between 0 and pi on 2, cos x is always less than 1. Therefore, the rate of increase of x must be faster than sine x, because its derivative is always bigger than the derivative of the sine curve. So if it's increasing faster, and they both started at the same point, then the blue line must be above the red curve, because it's increasing faster. Now, that shows us that x is bigger than sine x. As I say, I just looked at in between 0 and pi on 2. After pi on 2, Well, we know the sine curve's always going to be less than 1. It's never going to go above 1. But our blue curve keeps going up and keeps going up. So after pi on 2, x is always bigger than sine x. So combining the two together, we do get that x is bigger than sine x for all positive values of x. Okay, so we'll finish off with, well, that's a smaller handful, isn't it?